All right, good morning, afternoon, or evening, everybody. Welcome to the Meet EMIT, the newest imaging spectrometer on the International Space Station Earth Data webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Savings Time, so we're going to go ahead and get started here. What I'll do first is begin today's webinar with a few logistics. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or if you have any questions, what I'd like for you to do is enter those into the Q&A panel rather than the chat, and you'll find that located on the right side of your screen. If you don't see that, there are 3 dots at the bottom of your screen. If you click on that, you should be able to select the various panels. Okay, today's webinar is being recorded. The recording will be posted both to the NASA Earth Data website as well as to our NASA Earth Data YouTube channel within a week of completion. Once completed, what I will do is I'll send an email to all of the registrants and participants with the recording links, as well as a link to the presentation slide decks that are used within today's webinar. As far as timing is concerned, today we are going to do things just a little bit differently than most of our Earth Data webinars, and I know some of you are repeat participants. So we're going to allocate the same 1 hour to the presentations and live demonstrations, but today we're going to build in a 5-minute Q&A after each speaker's section. And then we will also include an additional extended Q&A session at the end for any questions we did not get to or address, but we will still maintain the same hard cutoff of 3:15 p.m. Eastern Time. All right, during today's webinar, we have 3 speakers. Our first speaker is Dr. David Thompson. He is the co-investigator for the Earth Surface Mineral Dust Source Investigation, or EMIT, science team at NASA's Jet Propulsion Laboratory. He will kick off this afternoon's event with an introduction. Actually, let me pull up the agenda here so y'all can see what I am referring to. All right, with an introduction to the EMIT mission and imaging spectroscopy. He'll then speak to data collection and provide you with some sensor information, such as the average revisit time and the spatial and spectral resolution. Finally, he will wrap up his segment with an overview of potential applications for EMIT data, and then we'll transition to the first 5-minute Q&A. From there, we will move next to our second speaker, Eric Bolch. He is a remote sensing scientist at NASA's Land Processes Distributed Active Archive Center, or LPDAC. He will provide you with an overview of existing EMIT data products and also show you how to find and access EMIT data using Earth Data Search. After this, Eric will highlight some of the EMIT data tutorials and other learning resources that can be found within the EMIT GitHub repository. After this, we'll transition to our second 5-minute Q&A session. Our third and final speaker today is Dr. Philip Broderick. He is a scientist on the EMIT science team, and he's also located at NASA JPL. Excuse me. He'll continue this afternoon's webinar with a live demonstration of the EMIT Open Data Portal, which is called Visions. Once his demo is complete, we will move to our final 5-minute Q&A period, and then from there we'll just kick it right into the extended Q&A session with a hard cutoff of 3:15 p.m. Eastern Time. And just a really quick note about the Q&A, we will try to address all of the questions within the time allotted, but if we are not able to address your question during each of the segment Q&As or the extended Q&A at the end, our speakers will follow up with you offline. With that, I am going to stop sharing my screen and toss the presenter role over to today's first speaker, Dr. David Thompson. David, and let me go ahead and do that really quickly. I'm going to stop sharing, make sure our polls are closed, because I won't be able to toss it over if they're not. So we've got, let me close the polls. And all right, you're sharing your screen. Perfect. Let's get started. Thanks, everybody.
Great. Thanks a lot, Jennifer. I'm thrilled to be here to talk to you about the EMIT mission. This is a really exciting new imaging spectrometer mission that was just recently launched by NASA. I'll tell you a little bit about the mission objectives and then the various analyses that are done as part of the standard EMIT mission, and then some of the other uses that you might find for EMIT data. before handing it off to our next speakers. I am the instrument scientist for the EMIT mission. I also serve as a co-investigator, but I'm speaking on behalf of a much larger group of individuals. Rob Green is the PI, Natalie Mahawald at Cornell is our deputy, and then there's a huge team here at JPL doing the management of the instrument, indeed the construction and operation of the instrument on board the space station. Yeah, without any further ado, let's talk about EMIT. And there's really no better single image, I think, that encapsulates what EMIT is all about than this one that you see here. This is a MODIS image, actually. It was acquired off the coast of North Africa a few years ago, but it elegantly shows this notion of mineral dust in the Earth system. You can see there are big dust plumes eroding off of this surface in North Africa and being cast out over the ocean. And the mineral dust plumes actually have two different colors, and it comes from the different source regions that the mineral dust is emitted from. You can see this lighter colored plume, and then this other terrain out here has a much darker colored plume. So mineral dust is actually a pervasive element in the Earth system. This is not just happening in North Africa, but it's really happening around the world, where in dry lake beds and playas and other arid land regions, wind is eroding dust, kicking it up into the atmosphere where it becomes a part of the Earth's atmospheric system, and it can have a climate impact. It can absorb or reflect solar radiation, but its properties in the climate system are really dependent on the dust's composition, whether it tends to have a lot of iron oxides like this darker plume, it can absorb a lot of solar radiation, or if like this lighter plume, it actually scatters radiation back out into space. So either of those two things can be true, and it's really the distribution of mineral dust composition that influences its total climate impact, whether it's a net warming agent or cooling agent. And we really don't know to date. So there's been a lot of work modeling this in Earth system models, but it really lacks the information about mineral dust composition. So EMIT intends to close that gap by observations from the International Space Station. So here's a cartoon that describes the process. From our vantage point on the International Space Station, the EMIT imaging spectrometer is going to map the geology of dry lake beds and playas and arid lands worldwide. It's not going to try and find the dust in the atmosphere, but rather to map the mineral composition of the surface. So instead of just getting a snapshot of what dust in the atmosphere is doing on any particular time or weather event, we're aiming for a process level understanding, which really starts with the mineral composition of these dust forming regions. We'll be providing those mineral maps to Earth system models that can then predict what the consequent composition of dust eroded from those areas will be, and whether it's a net warming or cooling agent, its radiative forcing impact on the climate system. And of course, dust has a lot of other impacts. Mineral dust can fertilize phytoplankton or plants in the Amazon. It can have human health impacts too. So there are a lot of other good reasons to learn about the mineral dust cycle, but our primary focus is to close this knowledge gap and understand whether dust is a net warming or cooling agent, over which there's quite a bit of uncertainty currently. And we'll do this, again, by measuring the geology of the surface. So we're going to be looking at mapping minerals on the Earth's surface globally from the perspective of the International Space Station. In addition to looking at these mineral dust forming areas, we'll also be looking at the adjacent lands. As you see here in this cartoon, we're looking at lands like agricultural fields or wildlands that are not desert, not dust forming now, but could become desertified in future climate scenarios. By understanding the mineralogy of these regions, we'll better understand the feedbacks that the mineral dust source could have on the Earth system if they become desertified later. So this will also provide more information to the climate models to better predict the course of the mineral dust activity in future climate. Okay, so what are EMIT science objectives? Fundamentally, to summarize, we aim to constrain the sign and magnitude of dust-related radiative forcing at regional and global scales, and we'll do this by acquiring and validating and delivering updates of surface mineralogy to initialize Earth system models. Our second major goal is to predict the increase or decrease of available dust sources under future climate scenarios, to run those models forward with the mineralogy that we provide to learn the consequent radiative forcing impacts. But I want to talk now a little bit more about the sensor, because the real magic here is the imaging spectroscopy, the technology that makes all of this possible. It's been used in planetary environments for a long time, but here we get to turn that same technology to Earth's surface to better understand the composition of our own planet. The EMIT instrument is a push broom design, which means it has a linear field of view on the ground. So you can see in this cartoon, there's a line on the ground, light from this linear field of view enters a telescope. It's imaged onto a slit and then dispersed off of a dispersive grating element where it's sorted by the photon's wavelengths, cast onto this detector array. So this two-dimensional detector array gives us a cross-track dimension and a spectral dimension, which means that at every point along this line, we get a full spectrum of illumination sorted by wavelength, and we can produce spectra that look like this. This is the radiant spectrum from Earth's surface, and you can see that it peaks in the visible range where the sun emits most of its energy. This is illumination intensity on the vertical axis and wavelength on the horizontal. And you can see that there also is a lot of structure in this spectrum. And this is related to all of the things that have happened to these photons and their path from the sun to the ground to the sensor. So we see absorption due to atmospheric gases. That's these sharp peaks here due to water vapor, oxygen. There's carbon dioxide out here. And then there are other subtler modulations of the spectrum that are actually due to the surface reflectance signal. So this wavelength range, it basically spans the entire solar reflected wavelength range. So all of the photons from the sun that are available for remote sensing, we capture and dutifully sort into these wavelength bins. And by analyzing the spectra, we can actually access a wide range of different processes in the Earth system. And I'll talk about some more of those later. But for the EMIT mission, we're primarily concerned with the geologic signals that are in these spectra. And of course, we get these at every point along this line, but what we really want to do is map mineralogy over wide areas. So in order to do that, we let the space station orbit over the Earth. So we push this linear field of view along the ground and accumulate spectra for all of these points. So this gives us a data cube where we have an image of the Earth's surface, and at every point in that image, we have a full spectrum. Apologies if you're an imaging spectrometer veteran and you already know all of this stuff. I don't want to presume any background knowledge here today, and promise I'll get to some of the juicy details shortly. Okay, so I alluded to this before, that there's actually a whole lot that happens to these photons in their journey from the sun. And so one of the critical parts of the EMIT analysis that we have to do before we can look for mineralogy is accounting for everything that happens in the Earth's atmosphere. And you can see this here in the difference between the radiant spectrum that EMIT measures at the top of the atmosphere. This is similar to what I showed you before, and the corresponding surface reflectance. So this is a critical difference that one has to wrap their head around to understand and use EMIT data. Although we measure the radiance at the sensor, what we really care about for the purpose of Earth surface studies is this reflectant spectrum, which represents, roughly speaking, the fraction of incident illumination at the surface that's reflected back in the direction of the sensor. And here we're seeing that for a vegetation spectrum. You can see the dip at about 690 nanometers, which corresponds to the absorption by chlorophyll. You see this green peak here at 550, which is actually what makes plants look green to our eyes, is that little feature right there. And then there are a whole bunch of other features of this spectrum that have to do with the species, the canopy composition, the chemistry of the plant's leaves, and how much water is present. And we can analyze all of those different geophysical phenomena by looking at features of this reflectance spectrum. And it's really the same thing for minerals. Minerals have different distinctive fingerprints that live in this reflectance spectrum. So the first part of the EMIT analysis is to interpret this radiant spectrum that we get at the sensor to try and understand this entire optical system. That is all of the atmospheric state and the surface reflectance that gives rise to the reflectance that we measured. Okay, so after that's done, we have a reflectance product, and we can look for mineral features in that reflectance spectrum, the distinctive fingerprints of different mineralogy. Here's an example from an airborne instrument that's very similar to EMIT over the Salton Sea, where we tested some of our algorithms. And you can see here overprinted on these reflectance spectra distinctive signatures due to various minerals, carbonates, kaolinite, goethite, and hematite are iron oxide minerals that manifest mostly in the visible range of the spectrum. And these features uniquely identify these different minerals. So this is a method that we can use to just look at the distribution of light in different wavelengths, and then by fitting models to these reflectance spectra, determine what's present at that location. So I'll show you this Salton Sea example. This was done by Roger Clark, a member of the EMIT team. Early on in the project, you can see this is the red, green, and blue image, but after we analyze all of the spectra at every point, every pixel in this scene, we can figure out where the minerals are and form a mineral map without ever even having to go down and touch the rocks. So here you see examples of montmorillonites, smectites. There's a bit of calcite hiding out in an outcrop. So this is all really useful stuff if you want to learn the composition of Earth's mineral dust forming regions. Okay, so here in brief is the EMIT data analysis chain, and this will be detailed in later talks, but I want to give you a preview here. I mentioned before it starts with the radiance at sensor, and then we do this, what's colloquially called atmospheric correction, to try and infer the surface reflectance spectrum. After that, we analyze the minerals in those reflectance spectra to come up with a mineral map like the one I just showed you. And from there, it gets a little bit more esoteric. We aggregate those mineral maps into an aggregate product called level 3 aggregated mineralogy, and this is the input to Earth system models. So this is the coarse gridded Earth scale map of mineralogy that the Earth system models need in order to infer the composition of dust that will come from these regions and also the future climate impacts. And then the final stage of this analysis is, of course, going to be the model runs themselves, which will also be delivered to the archive. So to date, we are working on delivering these lower level products, so the radiance, the surface reflectance, and the mineralogical maps available to public use. And in fact, for the vast majority of people who are interested in doing other kinds of Earth surface studies with EMIT data, these are the critical products that are already largely available. Okay, so more about the EMIT sensor. What kind of an instrument is it? Well, it's an imaging spectrometer. It's a design here at JPL based around a Dyson lens. So this is a very simple optical layout, which is actually good for an optical instrument. You want it to be simple in terms of permitting high throughput, high efficiency for our measurements of the Earth's surface, very subtle mineral features. Consists of just a couple of mirrors, a lens, and then a grating that disperses the light into all of its different wavelengths. The detector is a device that's kept cryogenic, so we keep it very, very cold in order to enable very sensitive measurements of the infrared wavelength range. And this instrument provides the whole solar reflected regime of 380 to 2500 nanometers at about 7.5 nanometer spacing. So very similar to many other airborne and space-based instruments in existence. It provides about 60 meters ground sampling distance on the Earth's surface for a 75-kilometer swath. So if you crack open an EMIT image, you'll find about 1,200 cross-track elements, each of which is 60 meters spatial sampling. Here's what the EMIT instrument looks like in both a computer-aided design model with the bare instrument that you see here, the spectrometer, the telescope that sits on board a deck of various electronics and power supply circuitry to provide power to the cryo coolers and control the instrument and read out the data and collect it and send it back to the Earth. So that's what all of this does. And then you can see it in its enclosure. This is designed to radiate heat and isolate the instrument thermally from its environment in the International Space Station. This is what it looks like in the lab when we were assembling it. Over a year ago now, you can see the aperture covered with a bit of foil here. That's where the light comes in and the spectrometer at the back end. But just to give you an idea of scale, this is about how large the instrument is. Here it is in the back of a Dragon spacecraft going to the space station. You can see it all boxed up there in this white material. And here it is finally installed on board the International Space Station after our launch in July of last year. So we're coming up on just about 1 year of being installed on the International Space Station. Here you see it with the robotic arm that installed us, a really harrowing process actually that took many hours to accomplish, walking us across the truss of the space station to our final installed home. But since then, EMIT has been doing fine. We're cooking along, acquiring lots of data. Here's our first light image of a place near Perth, Australia, and it gives you an idea of just the exquisite detail that we get of the Earth's surface. And to think that we have just a full spectrum of information for every one of the pixels in this image is really, really mind-blowing. Here's what the associated spectra look like. So you can see here, these are radiant spectra that have the distinctive water vapor features that we expect. Looks quite different depending on whether you're looking at soil or vegetation here with our chlorophyll absorption or water that's highly absorbing in the infrared. So we're seeing all of the features that we expect. To date, EMIT has acquired images over a large fraction of Earth's surface. So you see in blue, we are focusing mainly on North Africa, Central Asia, a few places in the Southern Hemisphere and the Western continental United States, with a few other calibration validation sites scattered around to try and better understand the way our instrument performs for some other targets as well. So this constitutes over 30,000 cubes at this point that we've collected and more every day. It's quite possible that in the near future, after our primary mission is finished, that we would consider modifying this mask to measure other regions outside this area where we're focusing now. But for the initial year of operations, we're focused like a laser on our fundamental objectives, which are Earth's dust-forming regions in these arid areas. So how do we know that the instrument is performing well? Well, there's a lot of vicarious calibration and validation activity. That is, field teams go out to a well-understood surface like this controlled surface here of Black Rock Playa in the western US. This is courtesy Ray Coakley at the USGS. They acquire data from the ground, and we compare that to the reflectances that we get from the space station to make sure that they agree. And in fact, they do. Here's an inner comparison in both radiant space and in reflectant space of the measurements made at the surface, and we're finding good agreement. This is actually quite typical of the agreement that we get for a wide range of vicarious calibration validation exercises, and this gives us good confidence. This close agreement between the ground measurements and the space measurements gives us good confidence that we're supplying accurate products to the community. Here are some examples of mineral maps that have been generated with EMIT. This is again from Roger Clark of USGS. This is a location in the Andes, an area where we didn't really expect to find this degree of mineral diversity. But you turn a new sensor on even Earth's environment for the first time, and you discover all sorts of new things, even about our own planet, that we didn't expect to find. Here's an area of just remarkable diversity in iron oxide content. Of course, the rocks look more or less brown to our eyes, but there's a lot going on in the infrared. Here is another set of minerals. This is in the 2-micron region where we see illite, muscovite, kaolinite, various calcites and chlorites throughout the scene. Again, incredible diversity in this relatively small geographic area. And of course, EMIT is sensitive to other things too. In order to do our mineral analyses, we have to control for the presence of other confusing materials like vegetation. So here you see a map of dry, non-photosynthetic vegetation and green vegetation as well. You can see the green vegetation following this riparian corridor here. And in fact, because of the sensitivity of the spectroscopic measurement, we can detect even small subpixel vegetation content because of the fingerprints that it leaves on the surface reflectance spectrum. Here's another scene from North Africa, again showing diverse 2-micron minerals in what appears to be a fairly homogeneous scene. And a wide range of hematite and goethite in that same area. Now, these iron oxide minerals are actually critical for the EMIT mission because that really determines the amount of radiative forcing that the dust will have when it enters Earth's atmosphere. A final example is Lake Mead here in the home in the United States. You can see there's, again, a wide range of iron oxides and 2-micron minerals in these seemingly homogeneous rocks around Lake Mead. And you can see even Las Vegas up there has a lot of interesting mineralogy around that as well. Okay, so if you're interested in looking at the EMIT data products yourself, I'd highly encourage you to get some sort of browser like the VSWIR software package, which is available for free from this URL, or alternatively NV, if you have an NV license and are able to do that. It's really the best way to look at these spectroscopic data products easily. When you look at the data products available on the DAC, you'll find a file name that looks like this, and I've color-coded it to indicate the different fields that provide you information about that data. There's the product level in yellow, the timestamp, which is a unique identifier for that product, which is in blue, the orbit number in red, and the scene number within that orbit in green. Let me quickly exit out of this presentation and do a quick demonstration to show you just what that looks like. So there's really no substitute for a real EMIT data product. So I've opened up an example cube here in the VSWIR software package to show you. You can see here we have an example of a spectrum. I've just clicked on this rock outcrop in the image and brought up a spectrum that has really different distinctive features here that we can already interpret. You can see a bit of a dip there. That's the chlorophyll. So there's probably some sort of green vegetation in this pixel. You can see an interesting mineral signature here in the 2-micron range, and probably some iron oxides here in the visible near infrared. So we can already start to interpret this pixel. Let's click around and find some other content. These green hills look interesting. You can see here that we have more green vegetation. There's some liquid water here in the near infrared, which is probably water in plant tissues. And you can see lignocellulose features here in the shortwave infrared. So this is woody stems and other non-photosynthesizing plant tissues. It could be fallow plants or senescent plants, or it could just be like dry plant material together with the green stuff. Let's keep clicking around. This looks like some sort of a lake or pond in the mountains, and you can see that it has a very different spectral signature. Here we have some phytoplankton or algae pigmentation going on, probably some backscatter due to particles in the water, but it's all happening in the visible range. In the infrared, water is highly absorbing, so it comes back almost zero in the infrared. Let's take a look at more of these rocks. I think around here, yep, there we go. There's another interesting mineral feature. So this is calcite, actually, or some other carbonate present in these hills here. And of course, there are other areas in the scene with their own distinctive mineralogy. Here we have iron oxides, right, that look red to our eyes. There's obviously something going on there. So again, a really rich data product you could explore for hours, even in a single scene. And of course, we're acquiring these scenes at, multiple scenes every hour, every day while we sleep. It's really a huge archive with lots of secrets to unlock. Before I leave, I want to talk about just a few of the other uses of EMIT data. Here's an example of snow analyses. So snow hydrology is another great application area, looking at changes in snow grain size that are present or obvious in the spectrum for here for snow and ice, which bears on snow water equivalent and melt rates and albedos and that sort of thing. So very interesting to water management people. Also, we have, of course, water quality analyses. You can see here the changes in our surface reflectance spectrum by increasing the phytoplankton content of the water or increasing colored dissolved organic matter, looking at different aquatic ecosystem applications. It's also another possibility with the EMIT data. And of course, vegetation as well, looking at agriculture, wildland regions, or terrestrial ecosystems. Changes in those plants and their properties and the composition of the surface also have distinctive fingerprints in the EMIT spectra that are there for us to analyze. So it's really an exciting instrument with a lot of potential. And with that, I'll close and take any questions you have before our next speaker.
Okay, thank you, David. So let me just get this timer started. All right, we do have a few questions. The first question is, and I believe this was in reference to the mineral map, what is the resolution of the image?
Yeah, the EMIT spatial sampling is 60 meters per pixel. So that's the pixel size in the image. But we're able to see subpixel features because of this spectral zoom capability, that it doesn't take much of a rock outcrop to leave a distinctive fingerprint on that spectrum. So by analyzing the depth of those absorption features, we can figure out approximately what the areal coverage of that material is, even within a pixel.
Okay, wonderful. Thank you, David. The next question is there data available for Madagascar?
I can't say offhand. We'd have to look in the EMIT archive to be sure, and we'll show you how to access that data. It's on the EMIT webpage. There's a browser that you can use to see the data and the coverage to date, and I believe Phil will talk about that.
Yes, very good. Okay, thank you. So the next question is, what was the reason to put the instrument on board the International Space Station rather than as a satellite in a sun-synchronous orbit? Are there advantages to the sun angle variations with the ISS orbit that you are exploiting?
That's a great question. So for our purposes, the sun angle gives us our signal. So it would actually, in some respects, be preferable to have a sun-synchronous orbit. But the space station offers other advantages. It gives us power, it gives us data, and it was easy to get a ride there. So really, there were other reasons why the space station was sort of the preferable place for EMIT, especially because most of the Earth's arid dust-forming regions are within the latitudinal band that's spanned by the International Space Station orbit. So for all of those reasons, we decided that the space station was the most cost-effective way for NASA to close this science question.
Okay, thanks so much. Moving on to the next question. Do you mind sharing what spectral library and matching method you're using for building these maps?
Yeah, I believe that the spectral library that we're using is based on the USGS spectral library, which is already public, and I expect that the specific spectra that are used for the spectral matching will be published. They will be made publicly available. And in fact, I should have said it before, all of the EMIT Science Data System code and the data used to produce those product levels is already publicly available on GitHub. So EMIT's been quite progressive in this respect. I think we've developed all of our code in the open, and if you want to reproduce any of our results or adapt it to some other sensor, you're free to do so.
Okay, great. We do have quite a few questions. So for those folks who asked a question, if we don't get to your question during this first 5 minutes, we will try to address it during the extended Q&A. Next question, do you think that this new instrument could have potential applications in volcanic activity monitoring?
That's a great question. NASA's been looking into this not just for EMIT, but for a future mission called the Surface Biology and Geology mission, which is slated to launch later in the decade. And they're looking at volcanic activity, volcanic precursors and predictions. The products of volcanoes is a major science question. One could certainly begin to look into those questions using the EMIT data sets. Of course, we're limited to the ISS repeat rate. So the ISS orbit, because it's a little bit erratic, doesn't provide provide always regular coverage over the same area as would be necessary to build up like a volcanic eruption predictive model or anything like that. But we can certainly look at volcanoes. We can certainly do geology on those areas. So I think there's a useful subset of questions that one might answer there.
Okay, thanks, David. Next question. How does NASA ensure the quality and accuracy of EMIT data collected from satellite missions or other sources? What validation and calibration processes are in place? And I think just speaking specifically to EMIT, because certainly all of our data products have a very robust calibration and validation set of processes in place.
Yeah, that's another good question. So we validate our products pretty much at every product level. So, and this involves both instrumented sites like the Railroad Valley Calibration Facility that emit overflies regularly, where we can compare our measurements from the space station to those made on the ground, but also specific field campaigns like the USGS campaign that I showed you before, where we can do those intercomparisons. And we're also looking at the mineral products as well. That's a much larger scale effort that's going to be a little bit more long term. But in the short term, I would expect to see the first published results on emit validation and intercomparison within a few months. We're closing those experiments out now.
Okay, thank you, David. We only have 10 seconds left, so I don't think we'll have time for this next question. So at this point, I'm going to transition the presenter role to Eric, and he can continue forward.
Thanks, Jennifer.
All right, Eric, give me just 1 second. All right, you should have presenter role at this point.
So, hey everyone, I'm Eric Bulch. I'm a remote sensing scientist with the LPDAC. That's the Land Processes Distributed Active Archive Center. And so during my presentation today, I'm going to talk about resources that the LPDAC provides and basically how to access and work with the EMIT data. And I am going to stop my camera to share some bandwidth, to save some bandwidth, because I'm going to do a couple live demos. And so just a little bit of background about the LPDAC. So there are several discipline-specific data centers that process, archive, and distribute Earth observation data. And we are the land-focused one, and we host and distribute data like EMIT. And so the first thing I'm going to kind of go through is I'm going to do a short walkthrough of our website here. I think Jennifer can share that link in the chat for everybody if they want to follow along, or you can get back to it later. So sort of when you first arrive here on our webpage, there's just some basic information about the LPDAC and like some news, such as that we have the webinar that we're giving right now. But I really want to focus on three of the things, three of these menus up here at the top. So for all data products that we provide, we sort of have a search catalog, and within that there's a product page that contains information about each specific data set that we host. And then we've also got a tools section that has some tools for finding data, such as Earth Data Search, which I'm going to talk about in a little bit. And then we've also got a bunch of resources.
Hey, Eric, we do not see the LPDAC website.
Oh, I'm sorry.
That's okay. So maybe just open it up as a separate tab and transition from the slide deck to just the native site. All right. Sorry for the interruption. Thank you so much, everybody. There we go. Perfecto.
Yeah. Sorry about that. Anyway, sorry. Back to the three menu options, sort of up here at the top. We've got like the data search catalog, which is going to have our product pages with detailed information about each product we host. And then we've got various tools that we link to, such as Earth Data Search, to find the data. And then also we've got some additional resources like e-learning materials, which would be like Python, Jupyter notebooks, things like podcasts, etc. The main thing on our website that I want to focus on, though, is the search catalog. And so if we're interested in one of the EMIT data products, we can search that here. And the results will show the three current products that we have, the L1B radiance, the L2A reflectance, and the L2B mineral identification product. So for each of these, we can see they're all cloud hosted with this little cloud in the top right corner. And so if we want to look closer at one of these pages, there's a lot of information about the product. Up here at the top, we've got like the short name, the long name, the PI, cloud information. And as you can see here, there's this huge banner in yellow. And right now, there are a couple granules that have been removed temporarily due to an issue. And I believe that issue is now fixed, and we're going to be making those available again soon. But anyway, you can get up-to-date information like that from this page, a general description, and some specific characteristics to the data set. Like here under collection and granule, we have information like the file formats, the coordinate system, average file size, the DOI, like pixel and resolution information. And then in the layers, we have more descriptive information about each specific layer in the data set. Things like the data type, fill values, etc. And then again, like the banner, there are some known issues that we've had, and so there's always going to be a record if there's been anything wrong here. So you can look back to make sure that the data you used was not affected by any issues with the data set. And then up here at the top, there's some more detailed information under the documentation tab. The user guide basically has all the information on this page and a bit more about how to work with the data. And then we also have the algorithm theoretical basis document, which is going to have detailed information about how the product is generated. For these other links here, there's some examples for working with the data under e-learning. These tutorials and stuff which are on our GitHub repository that I'll also talk about in a little bit. And then to access the data again, you can use Earth Data Search. That's the main tool to do that. And then lastly, like if you need to do cite the data set for a paper, you can select a style and it'll generate a citation for you here. Pretty handy if you're working with the EMIT data set. So I'm going to close out this window. And so, like I mentioned, there's sort of three tools for finding the EMIT data. I think that, and so that would be Earth Data Search, which I know I've mentioned. And then there's the programmatic way to use basically use Earth Data Search, which is the Common Metadata Repository API. And we have some resources that explain how to use that. And then there's also Visions, which Phil's going to talk about during the next section. And so Earth Data Search is kind of a one-stop shop for all NASA Earth science data sets. And I'm going to walk everybody through a quick search for some EMIT data here. And so let me open this link. And the first thing you're going to want to do after you get here is to log in. You do need to be logged in to download the data, although there's no cost or anything associated with it. So quickly, I'm going to log in to our demo account here. And if you don't have an account, there's a couple links here that you can use to register. And so after you've logged in here, and you can see this page, you've got some tools over here on the right to do like spatial filtering. You can search by spatial polygon, a bounding box, circle, or single individual points. Or you can upload a GeoJSON as well, just by clicking and dragging it into this map section over here. And then on the left here, you've got some other tools for filtering. The first thing we're going to do, since we're interested in EMIT, is just search for EMIT. And if we put it in quotes, that'll make sure we get exact results. There are a couple data sets that have the word emit in the description. So if you don't use those, you'll get a couple extra results here. And so these are the collections that belong with EMIT, or products, as we've called them. They have a little information button here where you can view the collection details. And that's going to have information like the DOI, the temporal extent, the bounding rectangle, a short description, and then some information about the cloud access, like we've got the region and the AWS bucket information. So if we go back and we want to focus, say, on like one data set, we can pick something like this estimated surface reflectance and uncertainty here. And this will take us to a page that shows all the available granules. So right now there's about 28,000 granules of EMIT data that you can use. And so we're going to go ahead and try to filter these down a little bit to find what we're interested in. So the first thing I'm going to do is use a spatial bounding box. I'm just going to select an area over Southern California. You can see that already narrows us way down to about 350 results. And then let's say we have a specific time range we're interested in. We can see down here along the bottom, this green line indicates when there are acquisitions for the data set. And you can see like this gap in May that was indicated by that yellow banner page. Hopefully that'll be resolved soon. But let's say we want to get all the data from this region in January of 2023. We can use this menu on the left to filter by date. Select the first and last days in January. That'll sort of narrow our results some more. And then one other nice feature here is you can also filter by cloud cover. So let's say we want to go for some really low cloud cover. We can put in something like 30%. And that'll filter us down. And in this instance, we've only got this one granule left. And so I forgot to mention this before, but a granule can basically be thought of as a single spatiotemporal scene. And so within that scene, there's a couple assets. There's a browse image, which you can get by just like clicking on this image. You want to open it in a new tab. You get a good look at the scene to see what's going on there. And then you can also directly from here just download the scene if that's all you need. And so here, there's 3 assets associated with this granule, and that's going to be the actual reflectance, the reflectance uncertainty, and the mask file. And so you can download each of those individually, or you can copy the AWS links if you want to access it from the cloud. Then lastly, we have this little drop-down menu here where we can view details about the granule, and this has the granule level metadata. And this has things like the start and stop time of the acquisition, whether it's day or night, the cloud cover, and the polygon that bounds it. So you can see all this sort of metadata information here. can't seem to get this to scroll back over, but there we go. You can see all that metadata information here. And you can also search using this metadata information if you're using the CMR API. So if we go back to our results here, there's one last feature I kind of want to cover in Earth Data Search, and that is adding it to your project. So here you can add this to your project with the plus button. And what that does is that allows you to search and find all the granules that you would be interested in. You can add them individually, or you can add entire collections to your project. And then up here in the top right, you can view your project. It'll have all those things listed, and it'll help you bundle them up to download. So if you click the done button here and download data, it'll bring you to a page that has some options. So on this download page, if you've assembled your whole project, all the granules you want, each asset for each granule will have a URL here, and you can either copy them or save them as a text file if you want to access it and use the tool to download it. Or if you want to use AWS to reach these, you can copy the links here or do the same thing with a text file. And then lastly, we have a download script with some instructions here. And you can basically download this file and execute it, and it'll download all the granules to a location for you. So that kind of concludes the basics of working in Earth Data Search. And so the last sort of thing I want to talk about today is our EMIT Data Resources repository. And so that's going to contain an Earth Data Search guide in case you want to look back at what I just talked about. And then it's also got a lot of helpful Python Jupyter notebooks that you can use to work with the data. There's examples of things like searching using the CMR API, how to utilize S3 access to open the data, how to orthorectify the data using the GLT that's included in the NetCDF, how to extract latitude and longitude point data and export it to a CSV, how to extract an area of interest, find by a polygon. Also, if you want to work in NV format, there's an example of how to convert to NV format, examples about quality filtering, and then also a couple interactive plots where you can look at the spatial data and hover over areas and see the associated spectral data in another plot on the side. And so we really do welcome contributions. We really want to embrace open science and sort of help build a community for people that work with our data sets. So if you look at this repository and you find some problems, please create an issue on the GitHub page. Or, if you want to contribute, feel free to submit a pull request. And, we'll try to be receptive to any feedback that we get. And then lastly, if you're not really that familiar with Git, feel free to just send us an email. This is our contact information. Were there any questions?
Yes. So just a word for all of our participants. What I'm going to do is just try to keep the session Q&A relevant to the last speaker. We do have some questions that are left over from our first presentation, and then we will address those at the end. So I did have a question about, gosh, I'm trying to get back up there, whether or not it had to do with APIs. Give me just 1 second here. I'm trying to locate it quickly here.
Sure.
Okay, can we use the API to get these data sets and display these data sets in a web-based decision-making tool?
So that is not entirely available. You can open and see the browse images. You can do that with the CMR API, or you can do it with, there's a tool called Earth Access that the National Snow and Ice Data Center put out that allows you to do that as well. And then there's some Python notebooks that show you how to stream the data after you find it. But that is kind of difficult as the EMIT net CDFs are very large.
Okay, thank you. Let's see here. There was another question that was just, okay, so the next question is, are there any plans to have EMIT data available on Google Earth Engine?
I am not aware of that. Perhaps Phil or David would have some insight to that. Right now, I don't think so.
Yeah, at the moment, I don't believe we do. Of course, we would have to work with Google in order to support that. If it's certainly something that we're open to. Again, all of the data are open access, so there's no restriction in ingesting them. It just hasn't yet been done.
Okay, well, thank you, Phil, and also thank you, Eric. So again, trying to keep the questions relevant to Eric's segment of the presentation, and so we may not use the entire 5 minutes, and then we'll transition on to Phil. The next question is, I'm a novice user. How friendly is EMIT for use with ArcGIS Pro or, oh gosh, this is the trouble with questions in the chat. It just jumped around here. With ArcGIS Pro or, excuse me. It's much easier to keep track when they're in the Q&A. I apologize. Well, why don't we address that piece while I'm trying to find this question. Okay, with ArcGIS Pro or QGIS. My apologies and thank you.
So I believe that you can open the data sets with those tools. However, I'm not sure. I do not have a lot of experience working with the EMIT data in them, and so they may be more difficult to use than something like NB or Python.
So we did have another participant, and thank you for this, type into the chat that Nmap box in QGIS can be used for EMIT level 2A data. So thanks so much for that additional feedback. That we appreciate it very much. All right, let me kind of take a hop back down to the Q&A here and see if there are questions directly related to Eric's presentation. Some of these were actually already answered with respect to the CMR stack API. And all right, bear with me, thank you. I think with this, okay, so there is a question, though I don't know, Eric, we'll give this a go. Pertaining to the greenhouse gas emissions, will there be any time to discuss the ISOFIT optimal estimation tools? Is the ISOFIT OE tool only available via Python at this point?
So I believe that's going to be a question for Phil or David. They're going to be able to answer that a lot better than me.
Sure. I think Phil may have answered that, and I'll parrot his response that currently ISOFIT is only available in Python. We're happy to follow up with you on any specific questions that you have about that software package. It is, as the others, openly available on GitHub.
Okay, thank you very much. I think with that, we're going to go ahead and transition to our final speaker, and then we'll address any questions that are still remaining once he has finished. All righty, so Phil, let me toss you the presenter role.
Excellent.
And thank you so much, Eric. All right.
All right, so I'm working on bringing up this here. If someone can confirm that you can see this, that would be great.
Yes.
Thank
you.
Excellent. Thank you. All right. Well, thank you very much. I'm really excited to be here today. My name is Phil Broderick. I'm the project algorithm scientist for EMIT and work closely with David and our colleagues at the DAC and the rest of the EMIT team to help work on providing some of these products for you. So today what I'm going to show you a little bit about is the EMIT open data portal called Visions. Now, the first thing that I'm going to say, even before we get into looking at this at all, is that the absolute trustworthy source of all data for EMIT is absolutely the LPDAC. And so if you go to Earth Data Search or and you look at anything there, that is the home and the host of all data that we're looking that we're going to be talking about here today. This is just a different visual portal to express some of that same data and to augment it with some other things that are in the process or coming quickly down the pipe or might be in a slightly different format than what is supported via Earth Data Search. So with that said, I'll go ahead and start sharing this tool. So this is what you'll see on the homepage of the EMIT Open Data Portal. There's this map here that we're going to be spending some time talking about, but I'll also just call out that there are some using the map details and FAQs down below that will answer and show some visual tools to some of the things that you might have questions with if I go a little bit too fast in the walkthrough here today. So the first thing that I'm going to note is when you come here, this might be a little bit small for your screen, so there's a full screen option. I'm just going to go to a different tab where I have that preloaded here. And you can see the same experience in full screen. So the first thing that you're looking at when you come here is a bunch of blue tiles, and then you'll see a couple stripes in the background of yellow tiles. Everything that you're seeing in blue is a scene from EMIT that has already been delivered to the DAC, and you can go and find radiance there. And everything in yellow is data that is in the process, that is currently being processed on our science data system and will be delivered to the LPDAC shortly. I'm going to start by going over here onto the left-hand side and selecting on some layers so that we can see a little bit about what is currently on the screen. And the first thing that you'll see is that we're looking at both the coverage and the current RGB mosaic. So I can slide around the screen. I'm going to go to the US here, and I can zoom in on some particular locations. And we can see the full RGB of the images, the full resolution RGB of the images along with the outline of the tile of the given scene. If I click on that tile, over here on the left-hand side under the info section, I can see a whole variety of different metadata for that tile. Things like the retrieved water vapor of the tile, the solar and sensor geometry, things like zenith and azimuth, the exact time that it was acquired, the estimated cloud fraction within the scene, etc., are available as different metadata. And then critically, you can see one-click links to the radiance, the observation file, which is the some geometry and sensor characteristics, the level 2A reflectance, and the level 2A reflectance uncertainty. You can also go find these as full links here over on the left-hand side if you prefer to find the full path length here. So I'm going to zoom back out for a small second. And the first thing that you're going to see when you look here is that there's quite a bit of data overlapping on top of itself. And that's because, as David described before, the trajectory of the ISS often repeats over the same ground position. So a useful thing that you can do is sort this data through time. So on the bottom here, there's a time slider, and you can drag that down to just a little bit. So I'm going to zoom in on only, let's say, the month of June. And these are all of our recent acquisitions just through June that are now displayed. If this view gets a little too coarse, you can go over here and you can use your mouse to just zoom in a little bit and see the explicit days being mapped. You can also set the time more precisely by clicking this and selecting through to the exact day and even time of day if you'd like. Now, some other things might pop out at you as you begin to explore some EMIT data, and I will just call them out briefly. So one, you'll see a bunch of wild colors being represented on the display. That's only because of the quick visualization that we're doing to demonstrate this. So this isn't a property of the underlying data, it's an artifact of the way that we're doing the visualization. So this section of the US is not purple. And if you go download those data, you'll be able to stretch them in any one of a myriad of different ways and see a more traditional RGB. That's one thing I'll point out. The other thing is that you'll point out that you might notice that there are a bunch of missing areas of data. That's because EMIT actually has an onboard cloud screening algorithm. And in areas where there are lots of clouds, it's a very conservative algorithm that's running, but in areas where there are lots of clouds, those data are excised and not downlinked. And so you might see these kind of gaps in the data, and that's just to manage bandwidth limitations on the downlink. All right, I'm going to go over to the left-hand panel, and I'm going to go back to the layers right now. And I want to point out a couple other layers that people might be interested in. One of those is the forecast tool. So for those of you who might be planning field work into the future or might be interested in timing any sort of coincident observation with EMIT, we put up the latest forecast for the next 8 days of acquisition here every week. And this usually goes up on Tuesday afternoon, sometimes on Wednesdays. And you can see if you hover over it, the date and the approximate location that data are going to be collected. Now, this is a forecast, so this is subject to any operational variations that might occur, both on the ground on our science data system or with our instrument operations team, or any of the ISS operations that might occur, such as altitude adjustments. So this is not an exact forecast, but it should give an idea of where data are going to be acquired. You can also see the target mask over here, which will be shown in red. Now, you'll quickly notice that there's lots of data outside of the target mask, and that's because there's a substantial buffer that's applied around that during the planning procedure. But you can get an idea of where EMIT will be acquiring data globally by toggling this mask on and off. And then anytime where the geometric constraints are met, we will acquire data over those locations. And we'll keep this target mask up to date into the future as it may change. The other thing that I want to call your attention to is in this coverage tile. So that's this layer that's currently being shown in blue. You can actually filter layers down. So I'm going to go over here and I'm going to actually choose any one of the properties that we might want to look at. So for example, I can go on down and let's choose the retrieved water vapor of the scene. So maybe I want to only look at scenes that are very dry for a particular reason. So I'm going to go ahead and set a threshold of 1.5, which is in centimeters squared there. And so we can see the when I hit submit, the number of scenes that were available went down. And if I continue to drop that number down, the number of scenes that are visible will continue to down select. And again, I can then go use this tool and do a one-click download. Alternately, if I'm interested in downloading just this layer here, if I hit this download button and then say export to GeoJSON, I will download whatever filtered data or whatever data is currently displayed in that coverage layer as a JSON file, a GeoJSON file that you can load into your favorite GIS software package. I'm going to very quickly, with the last couple minutes, show you a few other things that we're very excited about with EMIT data, because of course, there's much more than just the red, green, and blue imagery that we're showing here. The first of these is an example showing greenhouse gases, and there have already been some questions about this in the chat. So if you go over on the main site and you click on this greenhouse gas page, you'll see this view that I'm showing right here. And this shows greenhouse gas emissions, and particularly methane that we're looking at right now for a variety of regions. So not to pick on any one location, but here's an example identified methane plume from a point source emission that has been identified. And if you're interested in this whole process, we've done several webinars on those before, and we can get some more information there. But approximately, this is showing the maximum plume concentration within this methane plume, along with the scene ID. And again, you can click on this and go get the radiance data. We're working hard to deliver the actual methane core product, and those will likely be available on the LPDAC in the coming months. So you can see these observations around on the planet. Again, you can filter things through space and through time, just like we could before in the RGB data. And you can check this for latest concentrations. One last thing that I'll show you before I open it up for questions is a quick preview of where we're going. So we of course heard from David about the primary objective of the mission to quantify mineralogy across the Earth's surface for radiative forcing perspective. And so we have a sample of that over North Africa. Now, this isn't quite available yet, but will be in the coming weeks on the Visions portal, and this is what this can look like. So this is an example of mapped hematite over North Africa. This is just a subset of a location, and you'll see this isn't a complete mosaic, but this is a mosaic of a subset of the data that we have available that's already been processed to be cloud-free. And you can see the striking detail across the surface and the variability of this hematite signature. And we can look at this for a variety of different minerals. So this is hematite, but I'll bring up, for example, gypsum on top of that, and you can see a very different spatial distribution. Or here's an illite and muscovite distribution, for example. So really just some absolute stunning patterns across the surface, and our science team is working hard on continuing to refine and deliver this product, and we look forward to being able to share this with you very soon. So stay tuned for that. With that, I'll go ahead and stop sharing the screen, and I think I will turn it over for any questions.
Okay, well, thank you so much, Phil. So our speakers have done an excellent job in terms of responding to questions, both within the chat as well as within the Q&A with text response. And so I found one question don't think has been answered from the beginning. Let's address that first, and then I see a new question that's just come in. So the first question is, why are there two different mineral ID sets, and what are the differences? And I think this question was asked pretty early on while David was presenting.
Yeah, there are two different ID sets reported because there are two primary spectral ranges where EMIT detects minerals. One is in the visible range, and that's where the iron oxides show up, in the visible and near infrared out to about 1 micron. The shortwave infrared beyond that has all the other minerals. And so it's quite common for us to do detections independently in both spectral regions, and we typically report those minerals as separate maps because those two different kinds of minerals can all coexist in the same pixel.
Okay, well, thank you very much. So the next question is mineral abundance data included in the EMIT Level 2B Min version 1 NetCDF files?
I can take a stab at that. So the band depth, which is a measure of the depth of the absorption feature for both the 1 micron and the 2 micron features that David just referred to, are reported in that first delivery product. Now, we do plan on delivering a second L2B product in the near future, which will be a spectral abundance, which is where we are going to use some additional laboratory data in order to sort out from the detected minerals within the full spectral library down to 10 primary minerals that are useful for Earth surface modeling, or sorry, for Earth system modeling. And that's where you will see the things like the hematite and the goethite maps that I was just showing before. So that is a product that is to come. We're hoping to have that up in another month or two here relatively soon.
Well, thank you so much, Phil. So our next question is, let's see, let me just jump up a tad here. Okay, what are the future prospects for EMIT's mission? Are there any plans for potential enhancements or extensions of the instrument's capabilities, such as incorporating new spectral bands or exploring novel data fusion techniques with other space-based sensors?
I could take a crack at that. And I'll say that although the EMIT instrument itself is pretty much set in stone. It's installed on the space station, and that's not going to change. There's a lot of potential to use that instrument in new ways. There are a variety of instruments on board the space station, including ecostress, OCO3, for example, and others that are looking at Earth simultaneously with EMIT. And so as far as data fusion goes, I think that's a great prospect for future research that anybody can do. We're also looking forward to more instruments, other kinds of instruments that follow on the EMIT design with even better capabilities in the future. I spoke briefly about the SBG mission slated for later in the decade that will provide global coverage every 16 days with a 30-meter pixel, but otherwise be very similar to EMIT. So it'll have much better coverage, which will enable us to address a much wider, broader range of questions. So EMIT data still has a lot of potential. There's a lot we can do with it, but I think the next generation of instruments beyond will be even better.
Okay, perfect. And the next question is, thank you for the opportunity to pick your minds. I know that you have human analysts reviewing methane plumes prior to sharing them. Have you all observed any methane emissions over bodies of water, even if it's at a low confidence?
Do you want to take that one, Phil?
So I'm racking my brain as one of the reviewers of those products, and I think we don't have. I can't recall any explicit plumes that are shown over a body of water. Again, acquisitions over bodies of water are very difficult because of the complete absorption in the SWIR2 spectral region. You basically have to have glint on the surface in order to be able to see enough signature in order to detect methane. We do have some plumes that we know have traversed over some water bodies. I believe there's a case or two near some of the Mediterranean coasts where a plume passes over some bodies of water where there should be some pass there, but I don't believe that the detections are available there, again, because of just the absorption in the water region.
Okay, thank you, Phil. The next question is, have there been any cross comparisons of methane detection and probability of detection for point source imaging against any other imaging spectrometers? For example, GHG-SAT.
Yeah, there have not been any such experiments published yet. I'm sure there are folks that are working on that sort of thing, certainly.
Okay, thanks so much, David. And just for all of our participants, we have 4 minutes left in the extended Q&A. So if we do not get to your question, we will have our speakers follow up with you offline. Okay, so the next question is, are EMIT data normalized relative to sun angle, sensor angle, and time of day, or is that left as an exercise to users of EMIT data?
There's a lot in that question. We certainly do take the sun angle into account when trying to infer the surface reflectance. But the surface reflectance itself is a directional quantity, which means that the reflectance of a pixel that you observe will be dependent on the solar position and the observer position. A trivial thought experiment is to look at the bright sunlit side of a tree canopy or the shaded side. And you see two different brightnesses there. So it's still a directional measurement, and all of the reflectances that we distribute are directional. So there's often people in the community will do what they call BRDF correction, where they try and use models to simulate what the observation would have been at some other viewing geometry. We don't try to do that with the EMIT reflectance products. That's left as an exercise for downstream users, because it's really quite case dependent in terms of what modeling assumptions you'd like to make for that.
Okay, thank you, David. So the next question is, do you know if it is possible to track changes into the rainfall patterns, for example, ENSO reachability in South America? And I just wanted to say that, the speakers can address EMIT capabilities, but certainly there are other NASA data products that can absolutely track changes in rainfall patterns and, taking a look at ENSO. So I can certainly follow up offline if you'd like to email me, and I can put you in contact with those data centers and some of the data set links. But for the two speakers, anything further to add to that?
Yeah, I think in terms of rainfall patterns, well, yeah, it's a good question. It's not really a weather instrument. We don't observe rainfall necessarily per se. Obviously, the imaging spectrometer data product tells us a lot about water in tree canopies, so it could be used for that purpose, for looking at tracking droughts or drought stress and mortality and those sorts of things. And it's possible as to the tropics in particular that we'll extend our target mask in the future to enable those kinds of measurements, although we don't have very good coverage of the tropics yet right now.
Okay, thank you very much. I was just going to, and I'll try to include a link as well. Okay, we've got 1 minute left. We'll tackle this last question here, and then I will leave the virtual meeting space open, but we will log off from the audio component. How does EMIT's imaging spectrometer contribute to the field of atmospheric science, particularly in understanding the distribution and behavior of key gases and aerosols? There's really two parts to this. Are there any specific atmospheric phenomena or pollutant monitoring applications that EMIT is expected to significantly advance?
I've been talking a lot. Phil, do you want to go for that one?
Sure, I can make an attempt. So I guess I'll answer the second part of that first. I think EMIT is already having an effect in terms of mapping out greenhouse gas quantities. The combination of the very large swath width, large coverage area, and high spectral resolution is a bit of a unique capability. And so the methane and soon to be CO2 detections that are coming from that are I think of high value. Now there's a incredibly rich field of atmospheric science in general, and we are, I think, only scratching the surface of what the sensor is capable to do in terms of atmospheric aerosol quantification, which is really being done primarily for our surface reflectance retrieval. And so I think that this is an area where, especially going into the future, we'll be able to explore quite a bit, both in terms of aerosols, but in terms of other trace gas emissions and pollutants as well.
Okay, well, thank you very much, Phil. And at this point, we have reached the end of the webinar in terms of content and Q&A. But I will leave the polling question open, the polling questions, excuse me, another 10.5 minutes or so. And we really appreciate your feedback on those. And we'll also leave the Q&A and the chat open. If you think of something, I will be forwarding the Q&A and chat logs to our speakers. And with that, thank you very much to our speakers today, to Eric, to Phil, and to David for the content presented. We really appreciate it. And thanks to all of you for taking time out of your day to join us, your day or your evening or your very early morning. We appreciate all of you. All right, with that, any final remarks from our speakers? If not, we'll log off from the audio component and leave the virtual meeting space open an additional 10 minutes.
I guess my only comment would be gratitude. Thanks all for your interest in the EMIT instrument, and we look forward to seeing all the things you do with the data.
Excellent. Thanks, everybody. All right, we'll log off from the audio component now, and I'll leave the virtual space opened. All right, goodbye now.